In our discussions of polynomial functions up to this point, we have corresponded the notion of graphs crossing the x-axis with zeros. And that's just fine as long as we're limiting ourselves to the real number line. That is to say that if we have a function that has an x-intercept somewhere, then we say that corresponds to a zero of the function, it corresponds with a factor, and so on. Now, we want to expand the idea just a little bit because although it's true that if we have a parabolic curve, for example, whose vertex is above the x-axis and which opens upward, we have no x-intercepts and therefore no zeros of the function in the real number system. That's true enough. However, if we expand our thinking to complex numbers, it'll turn out that there is a direct correspondence between the number of zeros in a function and the degree of the polynomial. And that's the essence of the fundamental theorem of algebra. The fundamental theorem of algebra. It sounds pretty auspicious, doesn't it? And by the way, there's a fundamental theorem of arithmetic, there is a fundamental theorem of calculus, there is a fundamental theorem of geometry, in case you're wondering. But here's the fundamental theorem of algebra. It says that if f of x is a polynomial of degree n, where n is greater than 0, then this should be then f has at least one zero in the complex number system. And you expand the idea just a little bit and you find out that it has exactly n number of zeros. That is, an nth degree polynomial function has exactly n zeros. Now, we've talked already about the notion that zeros lead to factors. So this idea of n zeros in an nth degree polynomial function leads us to the linear factorization theorem, which says that if f of x is a polynomial of degree n, where n is greater than 0, then that function has precisely n factors. So we have an nth degree polynomial function. It has exactly n zeros and therefore exactly n linear factors. Now, this tells us about the existence of those things, but it doesn't tell us much about how to find them. Our idea now is to go after them, is to investigate for them. And we have already investigated using a number of techniques up to this point. Now, let's talk about some of the nuances involved in just what we know here about the fundamental theorem of algebra and the linear factorization theorem. We know that just basically if we have a very simple function like this one, we can factor it and we can identify the zeros as the values of x that cause each factor to become 0. Okay, that's easy enough. 2 zeros, second degree, 2 zeros, 2 linear factors. Now, look at this one. We have x squared plus 4. If we want the zeros of this, we set this expression equal to 0 and solve for x. Well, we'll subtract 4 on both sides, and now x squared is negative 4, so x is plus or minus the square root of negative 4. But remember, we're talking about imaginary numbers here as a result of taking the square roots of negatives, so we have plus or minus 2I as the values for x, as the zeros. Now, these then are our 2 zeros. We have identified the n number of zeros for this second degree polynomial function. But what about the factors? Well, factors are related to zeros in that the factors are x minus the zeros. So for 2i, the factor related to it is x minus 2i. For minus 2i, the factor related to it is x minus negative 2i, or x plus 2i. So here are our two factors. Here's an interesting situation. It's cropped up in the past. We would have a function like this. We factor it. We see that the two factors are identical. The zeros are x equals 3 and x equals 3. Now, in the past, we would say, gee, this only has one solution, or one x-intercept. Well, that's true enough. In a sense, one distinct one, but really it has two. It's just that this one has multiplicity 2 associated with it. You see, it occurs as a 0 twice. And so there are 2 zeros, they just happen to be the same. And there are 2 linear factors, you see, that happen to be identical as well. Here's another situation, x to the fourth minus 1. We begin the factoring process. X squared plus 1 times x squared minus 1. This is the difference of two squares, which factors easily to x plus 1 times x minus 1. We can identify the zeros associated with these two factors rather easily. But what about the zeros associated with this factor? Well, we would have to come out to the side and say, gee, I'd like to find out the value of x that will cause x squared plus 1 to be equal to 0. So we come over here and we do that. We say x squared plus 1 equals 0 and then solve this for x. Well, subtracting 1 on both sides and then by the square root property, x is plus or minus the square root of negative 1, but the square root of negative 1 is I. So we have plus or minus I. Now we slide back over here, and so our various zeros are these two and then those two. That gives us then all of the factors. If we have 4 zeros, we have a fourth degree polynomial function. These are our 4 zeros. We should have 4 linear factors. And they would be, well, let's see, we have 2 of them over here that are going to stay the same. But these, let's see, if I is a 0, then x minus I is a factor. And if minus I is a 0, then x minus minus I, or x plus I, is a factor. And I'll bring down these other two. So, a fourth degree polynomial function, 4 zeros, 4 linear factors. I do want to point out here, and we'll bring this up later, that the complex zeros happen to occur in conjugate pairs. That is, if plus I is a 0, then minus I is going to be 0. And we'll see that with more sophisticated complex numbers shortly. In our investigation of polynomial functions, we make some observations and some calculations. We made observations like the leading coefficient test, and we make some calculations like our synthetic division to identify zeros and factors and whatnot. Well, we're going to go through a couple more observations and calculations here in an effort to be able to handle more and more complicated polynomial functions. The next technique we'll talk about is called the rational zero test, and it works like this. Suppose we have a function like this. It turns out that just by observing and making a little calculation on the leading coefficient and the constant, we can determine all of the possible rational zeros. Now here's how the calculation is made, and I'll show you how it's used in just a minute. But all of the possible rational zeros can be calculated by writing all of the fractions possible using the factors of the constant in the numerator of this fraction and the factors of the leading coefficient as denominators of the fraction. So we have, let's see, factors of the constant. The constant is 10, so all the factors of the constant would be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And now in the denominator, we have factors of the leading coefficient. The leading coefficient was 5, so all of the possible factors, plus or minus 1, plus or minus 5. Now, we have a little list to go through here. We have all of these guys over 1, and then all of these guys over 5. That's the complete list. Well, we put all of these over 1, and we just have all of these items. So we have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Then we go through all of these over 5. Well, let's see. Plus or minus 1 over 5, plus or minus 2 over 5, and then plus or minus 5 over 5 is just 1. We already have it in there. Plus or minus 10 over 5 is plus or minus 2, and we already have it in there. Now we have this list of all of the possible rational zeros. And you might be thinking, well, why do we want to go through all of this trouble to identify possible rational zeros? Well, this is a test. This is a technique that you would use when you sort of bump into a need for it. And here's how you might bump into that need. Let's say that we begin with this problem to build a table of values. Now, here's our function, and let's build a little simple table of values just right up here. We're going to just start with an x and y, xy pairs, and let's just say x is 0. Now, if x is 0, all of these terms go out and we have 10. So when x is 0, y is 10. Now, what about when x is 1? If x is 1, then we have 5 minus 2 minus 25 plus 10. Let's see, 5 minus 2 is 3, 3 minus 25 is negative 22, plus 10 is negative 12. So when x is 1, y is negative 12. Let's put these points onto a coordinate plane. Now, just relatively speaking, 0 goes to 10 is just up here somewhere. And 1, negative 12, is down here somewhere. Now, with the intermediate value theorem, we know that there is a crossing in the interval from 0 to 1. So we have a 0 in here. And you know, zeros, if we can identify a 0, it can lead us to a factor, and that will kind of make the function a little more, a little easier to deal with. All right, so we are hoping that that crossing is rational. Now, to test whether or not we have a rational value for the 0 of the function, we can use the rational zero test to determine which items we test for. You see, there are an infinite number of rational values between 0 and 1. Which ones do we test for? Well, we use our rational zero test, and we realize that between 0 and 1, the values in that list that are possible would be simply 1/5 and 2/5. So that's all we need to try. All right, so let's go through and try those. We would have, synthetically now, we would divide by 1/5. And so bring down the 5. 1/5 times 5 is 1. Negative 2 with 1 is negative 1. 1/5 times negative 1 is negative 1/5. Uh-oh. Together we get negative 25 and a fifth. Uh-oh. 1/5 times negative 25 and a fifth is a mess. And when you add 10 to this business, you certainly don't get negative 10 here, you see, to collect to get 0. So this value is not 0. That's the point here. All right, so 1/5 is not a 0 of the function. Now let's try 2/5. Bring down the 5. 2/5 times 5 is 2. 2 with negative 2 is 0. That's nice. 2/5 times 0 is 0. Together, negative 25. 2/5 times negative 25, the 5 and the negative 25 cancel, leaving negative 5. 2 times negative 5, negative 10. 10 with negative 10, 0. So we do indeed have a 0 at 2/5. Now, not only does that tell us that at 2/5 we have a crossing, and therefore we can kind of draw this part of our graph, and we don't know how it behaves after this, but we can make some discoveries about that. The important thing here is that with this 0, we can go through and factor our function. Now, our function was a third-degree polynomial function, and when we snag out this factor, a linear factor that is composed of this 2/5, then we'll have the other factor will be a quadratic function. Now, the other factor is just right here. It's 5x squared minus 25. All right, so we can go through the factorization like this. All right, so our original function was this, and now with 2/5 as a 0, x minus 2/5 is a factor, and the other factor we read from the bottom of the synthetic division, and here it is. And now away we go with continuing to factor and identify zeros. I see a common factor here of 5, and I'll take that out. And now I'm looking to factor this. Gee, it's not the difference of squares. So I have to kind of solve it another way. I have to think this way. I have to think, well, what values of x will make x squared minus 5 equal to 0? Adding 5 on both sides, x squared is 5. By the square root property, x then is plus or minus the square root of 5. Aha, here are the other two zeros. So now I can continue the factorization. If these are zeros, they lead to factors, and so I can write those factors. On the way, though, I'd like to show you this, that a lot of times when a linear factor contains a fraction like this, you'll get a common factor in other parts of the function, like here. And it'll turn out a lot of times that that common factor can be multiplied through this binomial factor in order to clear the fraction. Here's what I mean. In this next step, if I multiply 5 times these two, I get 5x minus 2, you see. So I have a linear factor that has rational numbers. Well, actually it has integers as coefficients. And now this factors to, well, let's see, it's x minus each of these. So x minus the square root of 5 and x minus the negative of square root of 5, or x plus the square root of 5. So here then are our 3 linear factors and our 3 zeros. Well, let's make sure we understand what they are. Here are 2 of them, and the other one was found earlier as 2/5. So x equals 2/5 is that third zero. All right, so we have zeros and the same number of linear factors as we expected. Here's another situation where the rational zero test might come in handy. Suppose we begin with this function, and looking at the constant and the leading coefficient, they're both 1. So the possible rational zeros, that list is pretty limited because we have plus or minus 1 over plus or minus 1. So all of the possible fractions that can be made out of this would be plus or minus 1. Now, f of 1 turns out to be, and notice I'm evaluating f of 1 and f of negative 1 kind of by hand because there's no sense in going through the synthetic division process for this purpose. It's just too easy. So f of 1 means replace x with 1 and evaluate. We have 1 cubed plus 1, that's 3. F of negative 1 is negative 1 cubed, which is negative 1. And then with negative 1 and 1, we'll give negative 1. Well, how does this help us? Well, it turns out that, gee, if these are all of the possible rational zeros, neither one of them produces a 0 for our function. So how does this really help us? Well, we might notice here that that 3 and negative 1 are on opposite sides of the x-axis. So there's a crossing between these two. That is, if we're thinking graphically here, we think this way. We think, well, f of 1 is 3. F of negative 1 is negative 1. So there's a crossing within the interval. What about f of 0? Let's see what that gives us. Well, up here, if x is 0, these go out and we have 1. So f of 0 is 1. Aha, now we've narrowed our crossing to the interval from negative 1 to 0. Can it possibly be a rational zero that's in this interval? No, because we have tried our rational zero test here. We know that all the possible rational zeros are plus or minus 1, so we know that this zero is irrational. If we want to identify it, of course, we can use our calculator, put the graph onto the calculator and zoom in as many times as we'd like. But what we determined by using the possible rational zero test is that that zero is irrational. Here we have a 4th degree polynomial function, and as the functions get more and more complicated, what we're trying to do is identify enough zeros so that we'll be left with a quadratic factor. If we have a quadratic factor, we can deal with that in any number of ways. We can factor it using our normal methods, or we can apply the quadratic formula. But we'd like to kind of pick off the other factors all the way down to that point. So here, since we're starting with a 4th degree polynomial function, we need to try to bump into 2 factors so that we will, or 2 zeros, so that we'll identify 2 linear factors and therefore kind of whittle it down to 1 leftover quadratic factor. All right, that's the general idea. Now, we might think to ourselves, well, what's f of 0? Well, we can evaluate f of 0 rather easily, just putting in 0 for these x's, and it turns out to be the constant. So f of 0 is 14, and we might add 0, 14 to our table of values. And we might try 1. We would put 1 in place of these. That's pretty easy to identify too. All right, that doesn't turn out to be a 0, but it would contribute to the list of values in our table. Now, we jump into 2. We go to 2 maybe, and we would go through this process of synthetic division. Now, you'll notice that I didn't mention anything about using the rational zero test at this point, and I didn't do that because the list is rather large. I'm seeing that 14 is the constant here and 3 is the leading coefficient. So all of the factors of 14 over the factors of 3 would be a rather lengthy list, and so I would have a lot to check out. So all I'm doing is just kind of fishing around here at this point. Now, fishing around using 2 as a candidate as a 0, and dividing synthetically. Now remember that these entries come from the 3, the -5, the -23, 35, 14 from above. Bring down the 3, 2 times 3, 6, together here 1, 2 times 1, 2, together -21, 2 times -21, -42, together -7, 2 times -7, -14, together 0. Okay, so we have a 0, 2 is a 0, therefore x minus 2 is a factor. So we snag x minus 2 out of this, you see, and we have our function then becomes x minus 2 times this factor. Now this factor is identified at the bottom of the synthetic division. It is 3x cubed. Now notice the cube because it's 1 degree less than the original function because of this synthetic division process. All right, so it's 3x cubed plus 1x squared minus 21x minus 7. All right, now we're working with this function. And I can actually look at trying to identify the zeros of this factor rather than the zeros of the original function. And the reason I can do that is that any zeros of this factor will also be a zero of the original function. Now the one thing that you have to be cautious about in investigating a factor within a function is that when you identify an ordered pair, like if we said, okay, let's see if 3 is a 0 of this, or something like that, and it doesn't turn out to be a 0. Let's say it turns out to be that f of 3 for this factor turns out to be 10. Well, the ordered pair 3, 10 is not an ordered pair for the original function. It would be an ordered pair for this factor, but it doesn't contribute to the list of ordered pairs for the original function. So right now we are strictly on a quest for zeros of this rascal and not contributing to our list of items in our table of values. All right, now what I'm noticing about this one is that I have a prime number here and a prime number here. You see, and therefore the possible rational zeros is rather limited. So the possible rational zeros might be helpful for me in this process because there are so few of them that I can try all of them perhaps and bump into a 0 right quick. All right, the possible rational zeros, all the factors of the constant over all the factors of the leading coefficient. That means the 1 and the 7 are both over 1. That means plus or minus 1 plus or minus 7. And then the 1 and the 7 are over 3. So when 1 is over 3, that's 1/3. It's plus or minus. And when 7 is over 3, that's 7/3. Now I'm going to take sort of a path of least resistance here. I just want to try these, try the easiest one first. Now I've already looked at plus 1. You see, I kind of visually a little while ago. Minus 1 I could look at. I could do this synthetically. That might be a good candidate to start with. 7 is a pretty big number and the synthetic division could get out of hand. But this is pretty easy to do. So let's go through and divide synthetically. Now we're dividing synthetically into this factor. So we're going to use in our synthetic division 3, 1, -21, -7. The synthetic division goes like this. Oh, by the way, just for completeness here, I am going to do the -1. Now remember, the 3, 1, -21, -7. So -1, bring down the 3, -1 times 3, -3, together -2. -1 times -2, 2, together -19. -1 times -19, 19, together 12. So not a 0. All right, then 1/3. Bring down the 3. 1/3 of 3 is 1. That's nice. 1 and 1, 2. Uh-oh. 1/3 of 2. 1/3 times 2, you see, is 2/3. And then 2/3 with -21 is -20 1/3. Messy, messy, messy. 1/3 of this, oh, it's roughly -7. And so this just isn't going to work out. So we're not going to get a 0 there. -1/3. Bring down the 3. -1/3 times 3 is -1. Together 0. -1/3 times 0 is 0. Bring down or collect here to give -21. -1/3 times -21 is 7. And so -7 with 7 is 0. So now we have bumped into a 0. And that the rational zero test has been particularly helpful to us in this investigation. Okay, so if -1/3 is a 0, then x minus -1/3 or x plus 1/3 is a factor. So we can come back over here and continue the factoring process. And I'll do that right under here. So we've got, now I'm going to use the entries at the bottom over there in just a second too, but I've got this. I've got the x minus 2, linear factor that we've already identified. Now, this is x minus negative 1/3 or x plus 1/3 as another linear factor. And another factor, not linear, but another factor is we get by looking at the entries at the bottom of the synthetic division. There was a 3 over there, a 3, a 0, and a negative 21. So it's 3x, let's see, to the second power, 3x squared, and then 0x, and then minus 21. All right, notice the common factor 3 here. I'll snag that 3 out of there. And that's real nice because it'll kind of go with this other factor to give me some stuff that's not fractional. All right, so the 3 comes out, and we have 3 times x squared minus 7. And now I'll multiply the 3 in this other factor just to clean that up a little bit. Three times x, 3x. 3 times the 1/3 is 1. And then the x squared minus 7. Now, we ought to be getting more and more familiar with this kind of situation where we have a non-square in this position, and we will very quickly be able to imagine the factored form of this. But just to go through the routine one more time, it's the idea of setting x squared minus 7 equal to 0. And so x squared is 7, and x then is plus or minus the square root of 7. And then x minus each of those is a factor. You see, so it turns out to be, let's see, the factored form here is x minus the square root of 7 and x plus the square root of 7. Now the zeros here, we should list the 4 zeros. We have 4 linear factors. We should have 4 zeros. The zeros are x equals 2, x equals the negative 1/3 that we identified earlier, and then the 2 zeros that are identified over there, x equals plus or minus the square root of 7, so our 4 zeros. Consider this problem. Now we're going to dash through this one right quick. If we were looking at this, we would try to factor, oh, nice, we have 4 terms. We can factor by grouping, it turns out. From these 2 terms, I take out a common factor of x squared, leaving x plus 3. From these 2 terms, I take out minus 5, leaving x plus 3. Now I have this term and this term, which have a common factor, x plus 3. I pull x plus 3 out of this term, and we're left with x squared. Pull x plus 3 out of this term, I'm left with minus 5. Now we have that situation we had before, where we can actually factor this right quick. It's x plus root 5 times x minus root 5, and our zeros are negative 3, plus or minus the square root of 5. Now, this square root of 5, and we've bumped into irrational zeros a number of times, and identifying them can be accomplished algebraically and can be accomplished using the graphing calculator. I want to show you how we do that here. Now, algebraically, when we bump into the square root of 5, if we want a useful number for the square root of 5, we would have to evaluate the square root of 5 on the calculator. And since it's irrational, it's a never-ending, never-repeating decimal. So it just kind of goes on and on and on. And we have to decide the degree of accuracy that we want in our problem to decide where we kind of round off in this number. We certainly probably wouldn't need this much accuracy. Maybe we need accuracy to the thousandth place, maybe to the hundredth place. But we can find this same accuracy by using the graphing calculator. Let's have a look. The function has already been entered. Now notice to enter x cubed, we have x and that exponent key and then a 3. This is x cubed. And then 3x squared. The squared on x can be entered in 2 ways. It can be entered as an exponent with a 2 in this position, or by simply pressing x squared for this item to come up. All right, the graph on standard settings will look like this. It may be helpful if you're looking for zeros in this environment to first try to bump into zeros by using friendly settings. And we can get to the friendly settings very quickly by pressing zoom and then item number 4 or item number 5. Item 4 gives z decimal, and that means we have decimal values when we press trace. Now here's 0, and I'll just trace over to the left until we can see the blinking icon. And here it comes. Now, as we press to the left, I'm trying to find a spot where I have an x value and then a y of 0. And I'm noticing here the y value is negative and then positive all of a sudden, so I'm sort of straddling a 0 here. All right, now that just tells me that that 0 is between negative 2.2 and negative 2.3, which we know to be the case from the work that we just did on the board. But as I continue to cursor to the left, I do land on a 0 here at x equals negative 3, as we expected from before. Now let's try to get some accuracy on finding the 0 that's in this neighborhood. One way to do it is to zoom and trace. Now we're going to zoom, and if we just cursor down to zoom in and press enter, then the calculator gives us a little blinking icon where the icon was before. Now this is an icon that doesn't stay on the graph. It's actually just a centering icon, and it will give the center of the picture when we zoom in. So we want to zoom in at approximately this spot, so I'll press enter. Now notice that here's the centering icon, and I'll move it up just a little bit so we can see a little better. Now I'll move it to the right, and I'll press enter again, and that just means that we're going to zoom in again. And I can just do this any number of times that I want to do it, just for greater and greater and greater accuracy. And by the way, those XY pairs down at the bottom are positions for the centering icon and not positions that are on the graph. Let's go to the graph by pressing trace. This places the icon right onto the graph. Now we have negative 2.2375, and the y value is positive. I'm going to cursor to the right, and I get a negative y value, and it's very small. That y value is in scientific notation even, and we notice that the x is negative 2.2359 and so on, and I've gotten more accuracy than I need for rounding to the nearest 100th. Notice that the first several digits, as I straddle the intercept here, that I'm getting no change in the first 2 digits, and so I'm fairly safe in rounding off to 2.24. For greater accuracy, I can continue this zooming in process at this point if I wish to do so, and then of course at that same kind of point on the other side of the y-axis for the positive square root of 5. Now there is another way to proceed here to get a 0 very quickly. Let's press zoom and then number 6 for the standard settings. And now I'm going to press second and then the trace button. Now I'm accessing the calc menu here, and here's the menu that comes up. I want number 2. I'll cursor to it and press enter, or you can simply press number 2. But now it says lower bound, upper bound. Well, it's asking for us to sort of straddle the point. Now I'm going to go over here to the place where it's near the positive. There's my icon. All right, I want to be lower bound. All right, I'll press enter here for this lower bound along this particular little interval, and here's upper bound, and I'll press enter for this one. Now guess, don't worry about that. Let's press enter once again, and it's giving us a rather exact value for this x-intercept, 2.236068. And it's a very close approximation of the square root of 5. And we did it just by entering the calc menu. Well, before we leave this topic, I'd like to show you an interesting technique related to the zoom and trace technique that we looked at earlier. I almost forgot to tell you about this, but it's really neat. Let's get into that idea like this. I want to zoom in on a certain spot, and I'll just press zoom and then item number 2. And now I have the centering icon that we had earlier, and I'll just begin to zoom in on what I think to be a 0 or an intersection point. And I'm just going to move the centering icon around and press enter a few times. Now in this situation it might be helpful if we could actually see tick marks
corresponding to the degree of accuracy that we're looking for. For example, if we're trying to find x with an accuracy, this 0, to an accuracy of the nearest hundredth, for example, then we could press Window and then cursor down to where it says X scale and enter 1/100th. And then we'll create a tick mark at every hundredths position. And now I'm going to get back into, I've lost the idea of, that's the centering icon that I had before, but I'm not actually zooming in right here until I press zoom and then item number 2. There we go. Okay. Now notice the tick marks at every hundredth, and so, and let me make this abundantly clear here by going in one more time. You see, we've got a tick mark right here, and we've got one over here, and it looks like the graph is a little closer to this one. And it turns out that if I cursor over to it, now this is just the centering icon, I'm not tracing here, but and I'm not on the graph obviously, but this centering icon is right about at 2.24, and over here on the other side should be 2.23. You see, this is at 2.23. So the graph is clearly between 2.23 and 2.24. And we can see by observation that it's a little bit closer to the 2.24. We can do the same thing if we are trying to estimate the 0 to the degree of accuracy of 1,000th. We can just go Window and down to 0.001 and then Graph. And then we'd like to zoom in. I'm pressing number 2, and I have a centering icon, and those little tick marks now are at the thousandths positions. So I can very easily now see that this graph is going very nearly right on top of 2.236. You see, that's where this is, and the next one over is going to be 2.237, right about in here. And so it's pretty easy for us to see where we are using this, this X scale feature of the calculator.
Here we have a third-degree polynomial function. We'd like to identify the 3 linear factors and also the 3 zeros associated with this function. We would begin the process by perhaps thinking, what is f of 0? Well, when x is replaced with 0, these terms go out and we have -10. Now, f of 1 is pretty easy to identify just visually. If x is replaced with 1, we would have 1 minus 6 plus 13 minus 10. Collecting, we find that value to be -2. So 1 goes to -2. Then we would look at this little table and we'd think, well, let's see, 0 is at -10, 1 is at -2. The graph is sort of approaching the x-axis. Maybe we get some mileage by investigating at 2. Well, let's see. Investigating synthetically, 2 in 2. Now, the 1, the -6, the 13, the -10. Let's see, bring down the 1, 2 times 1, 2. Together here, -4. 2 times -4, -8. Together, 5. 2 times 5, 10. And with -10 gives 0. So we do indeed have a 0 at 2. So we have a 0 at 2, and x minus 2 then is a factor. So we can go through and factor. And the leftover factor we just read down here. This is 1x squared minus 4x, then plus 5. And now we would look to factor here. Well, we would investigate as we will, but we find out that we can't factor using the methods that we've been talking about. And so we need to find the zeros by using the quadratic formula. So using an a value of 1, b of -4, and a c of 5, we come over to the side and we apply the quadratic formula. Write the formula down, replace within it in the next step. Now notice that b is -4, so this is minus -4. You see, the opposite of -4. Plus or minus, b squared is -4 squared. Minus 4 times a is 1, c is 5. In the denominator, 2a means 2 times 1. Now let's begin to evaluate. Minus -4 means 4, plus or minus. Now, under the radical, we get -4 when the smoke clears on that business. Now, the square root of a negative number, well, we have to be a little cautious here. We're talking about an imaginary value here, so our answers are going to be purely complex. All right, let's go through the process, though. The square root of negative 4 is, let's see, the square root of 4 is 2, and the square root of the negative 1 is I. So we have plus or minus 2I. Now, 2 divides both parts of this numerator, so we can simplify to 2 plus or minus I. Now, we've identified all of our zeros. Our zeros are 2 plus I, 2 minus I, and 2. You see, those are our zeros. But let's go through the factorization. Now, the 2 plus or minus I zeros give us factors as x minus each of those. So if we want to write a factored form, then we're writing it this way. Now, for the other zeros, it is x minus 2 plus I, x minus 2 minus I. Kind of getting jammed with this other problem here. Let me erase this. So that's the idea. And now we just simplify. We just clean up a little bit in those brackets. You see, and we can just drop the parenthesis, change the signs, drop the parenthesis here. So this is x minus 2 minus I. And here is x minus 2 plus I as our 3 linear factors. And notice that the complex zeros, the 2 plus or minus I, will kind of naturally, in the flow of things here, appear in conjugate pairs. And that is universally true, that complex zeros occur always in conjugate pairs. Here we have a third-degree polynomial function, and let's say we want to find the zeros, and we're given one of them. We're given that 5 plus 2i is a 0. Now, we have a third-degree polynomial function, so there are only 3 zeros to find, and we know that since we have a complex zero, that complex zeros occur in conjugate pairs. So if 5 plus 2i is a 0, then 5 minus 2i is also a 0. Now, there are actually 2 tactics that we can use to find that third 0. One is kind of a graphical and analytical strategy where we begin the graph, we look for a certain crossing, and we use the techniques that we've talked about already. The other would be a purely algebraic strategy where we reason this way. We think, well, gee, if we have 2 zeros, then we know that we have a couple of factors, x minus that and x minus this are both factors. And if we have those factors, then the product of those 2 factors then would divide this polynomial evenly. And we could go through that division process. Now, either way we do it is okay. Let me backtrack just a minute, though, and mention something about this complex conjugate idea. That I mentioned, said something to the effect that if we have one complex 0, then we have its conjugate as a 0. Actually, it's true that all of the zeros that we have found in this entire section, and indeed in this entire development of mathematics, they've all been in the set of complex numbers. It's just that when we mention something like a complex 0 like this, it means that we have in this complex number, this a plus bi form, that the b value is not 0. Generally, we try to describe numbers in certain sets in the most efficient way. If we were talking about the number 5, we might call it an integer or a natural number or something like that to narrow the set from which it comes. And here, when we talk about complex zeros, we're talking about a complex number, a number which has an imaginary part that's not 0. Okay, just to kind of clear that up. Okay, let's take that algebraic approach now. Here's what we know. We know that these 2 are zeros, so we know that x minus each of these is also a 0, and their product, you see, will divide that. That's the idea. So I'm going x minus and then 5 minus 2i. Now, to clear this up, we have, let's see, x minus 5 minus 2i, and then x minus 5 plus 2i. There are actually a couple of ways to accomplish this multiplication. We could think of ourselves as having a binomial minus 2i, same binomial plus 2i. So the sum and difference of the same two terms, you know, use that kind of strategy if we wanted to. But I'm going to use the old way, the kind of long way where we just multiply every term here times every term there. So we would have, let's see, it's going to be a pretty long string of terms. X times x is x squared. Then x times minus 5 minus 5x. X times 2i is plus 2xi. Then minus 5 times x minus 5x. Minus 5 times minus 5 is 25. Minus 5 times 2i is minus 10i. And then minus 2i times all of these. Minus 2i times x minus 2xi. Minus 2i times minus 5 minus 10 minus full plus 10i. And then minus 2i times plus 2i is minus 4i squared. Now I'm getting into this other problem here, but I think we can follow what I've got. It's kind of like here's a border. I'll erase it in a few minutes. All right, let's come back and collect some like terms. Let's see. I've got no other terms that are x squares, so I'll bring down x squared. We should get some nice cancellations here. Let's see if we don't. Minus 5x minus 5x, that's minus 10x. I have no other x terms. So minus 10x. Now to try to keep track of things, I've already used this one. I've used those two. Let's see. 2xi minus 2xi. Ah, good. They take each other out. We have 25 here. And we have minus 4i squared. Remember, I squared is negative 1. So we have negative 1 times negative 4. That's 4. So 4 and 25 is 29. So those terms go out. We have minus 10i plus 10i. Those take one another out. And here is our polynomial product. Now, it should be the case that this polynomial will divide that one evenly, and the quotient is going to be kind of the leftover factor that will give us that third zero. Okay, let's see if that's not the case. Now, I'm going to just erase up here. I need some room to do the long division, because we're dividing now a polynomial with 3 terms into a polynomial with 4 terms. So we can't use synthetic division. You see, that's out of play here. Synthetic division works with first degree binomials with a leading coefficient of 1, so we have some limitations there, but it's still a very powerful tool. Let me get rid of all of this stuff as well as I can. Okay. So we're dividing x squared minus 10x plus 29 into all of this rascal. Now the division, if we've done our math correctly to this point, the division has to go evenly. I mean, just by the nature of the idea that we've been given 2 zeros, you know, and if we're sure that that is the case, then this should go evenly. All right, we're dividing. Let's see, first term into first term here, we have x squared into x cubed goes x times, so I'll put the x here. And now I'll multiply back. X times x squared is x cubed, and then x times minus 10x is minus 10x squared, and then x times 29 is 29x. And then we draw the line and subtract, which means that we change signs and add. This situation is trivial. We're going to change this sign to plus, change this sign to minus. Let's see, 7x minus 7x squared plus 10x squared is 3x squared. And then minus 29 with minus x is minus 30x. And then away we go with the next part of the division. I'll bring down the next term, and here we go. We have x squared into 3x squared goes 3 times. So 3. Then 3 times x squared is 3x squared. 3 times minus 10x is minus 30x. And 3 times 29 is 87. And then we draw the line and subtract, changing the signs and collecting. We see that we have 0 for our remainder here as expected. So x plus 3 is that leftover factor, and x equals negative 3 is the third zero. Let's talk about a couple of other strategies that can be brought to bear in analyzing polynomial functions. Now, we've already looked at a number of situations, the leading coefficient test, for example, and we've used synthetic division quite a bit. This is called Descartes' rule of signs, and it allows us to establish the possible number of positive and negative zeros, real zeros, in our polynomial at hand. If we have f of x is this is what we do. We're just looking at a sign pattern here. This is a rather intriguing thing. We look at all different kinds of aspects of these polynomials to get different kinds of information, and this is one that's rather intriguing. We're looking at its sign changes here. Now notice we have minus and then plus. That's a sign change. Plus to minus, that's another sign change, and then minus to plus. So we have, let's see, one sign change here, we have another sign change here, and we have a third sign change here. Because we have three sign changes, there are three possible positive real zeros. Now, I say possible because it changes. It's either 3 or 1. Now, 3 or 1, why is that? Well, it's like the analysis here is in terms of pairs of zeros. So it's 3 or 1 positive real zero. Now, so we know that there'll be at least one, you see, positive real zero. Now, this allows you, in certain situations, it would allow you to realize that if there's 3 or 1, then that means that there is at least one, you see, real zero, and that means real x-intercept, real crossing of the x-axis, that kind of thing. So graphically, we would look for a crossing, and there is either 3 crossings or 1 crossing, you see, in the graph of this function. So it kind of tells us those kinds of things. When this becomes important when there is a great mystery about the zeros of a polynomial function. Sometimes when they get to be of higher degree, the things that you need to do are rather elaborate. And this is just another item in the mix of things that we can bring to bear to solve those mysteries. Okay, now, on the negative side, to determine the negative real zeros, the number of negative real zeros, you find f of negative x. You just evaluate f of negative x. Now, you know what that means. In the f function, replace x with negative x. So all of these x's up here are replaced with negative x's, and we simplify to this. And then look at the sign pattern. Well, we have plus, 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 plus. No sign changes, and therefore there are no negative real zeros. So no negative real zeros. Now, here's an intriguing thought about this problem. If this is a third-degree polynomial function, we know that there are 3 zeros in the complex numbers. Now, it is either the case that all 3 of them are positive real zeros, or we have 1 positive real zero and 2 complex ones. You see, because we don't have any negative ones, we don't have any negative real zeros. So by this analysis, then we can make kind of some decisions about the nature of this function and its graph. Here's another situation. Here's a rule that will limit the number of possible trials that we make, either positively or negatively. It's called the upper and lower bounds rule. And it works like this. Suppose we have this function, and suppose we're investigating for zeros, and we find f of 0 to be 9, and we can do that by observation. And if x is replaced with 0, then we have simply 9. F of 1, again, by observation, we can determine that f of 1 is 2. Now, it might look like to us that we have, let's see, 0 goes to 9, and 1 goes to 2. So that graph is coming toward the x-axis, and so we're thinking, well, maybe we have a crossing here pretty soon. Let's try f of 2. Now let's do that using synthetic division. So we would go over here and put down the coefficients and the constant and bring down the 2. 2 times 2, 4, with negative 3 is 1. 2 times 1 is 2, with negative 6 is negative 4. 2 times negative 4 is negative 8. 9 minus 8, 1. Well, let's see, 2 goes to 1. All right, we're not quite there yet. Maybe we get there at 3. Let's see. So we bring down the 2. We have 3 times 2, 6. 6 minus 3, 3. 3 times 3, 9. 9 minus 3, excuse me, 9 minus 6 is 3. 3 times 3, 9. 9 and 9, 18. Uh-oh, we're going in the wrong direction here. Now, do we continue to try? Do we try 4 and 5 and 6 and so forth? Well, gee, we could analyze this and think, well, maybe there's a crossing, maybe there are a couple of crossings sort of in one of these intervals right in here to where we have 2 zeros within a really tight interval. You see a integer value interval in here, and so we might try this idea of the rational zero test or something like that. But the notion is that we could try positive integer values until we get really tired, you know, up to 10 and 12 and so forth, and these numbers will get out of hand. But the upper and lower bounds rule will allow us to limit those number of trials right quick. Whenever we see that all of the signs here at the bottom of the synthetic division are positive, it tells us that this is an upper bound for the zeros of the function. Upper bound for the zeros of the function. That is, there are no real zeros. There are no zeros to the right of 3. That is greater than 3. Now, if 0 occurs down here, 0 can play the role of either a positive value or a negative value in this analysis process. So just kind of bear that in mind. Now, just for informational purposes, on the negative side, there is a lower bounds rule as well. Suppose we're dividing on the negative side and we divide by -2. And this just illustrates the sign pattern that needs to take place if we have a lower bound. And it's an alternating sign pattern. It's plus, minus, plus, minus. And when we see that pattern on the negative side, it means that this negative value is a lower bound, and there are no real zeros that are less than -2. So we might as well stop the investigative process at that point. Well, you know, we have Descartes' rule over here, we have upper and lower bounds, we have rational zero test, we have leading coefficient test. We have all of these different processes that we bring to bear in analyzing polynomial functions. And yet, we have a graphing calculator, and you may think to yourself, well, gee, why don't we just pop it into the graphing calculator, use the zoom feature on the calculator, and get as much accuracy as we want concerning the zeros of a polynomial function. Well, that's not all that this is about. That is, you might be thinking, well, why are we even doing this? If we need zeros, we can get them right quick. But it's not just zeros that we're learning about here. And I would agree that the question about why do we need this is a valid one. And the answer, I think, is important. And it has to do with structure. And it has to do with what you're learning here in addition to just how to find zeros. You're learning how to take a rather comprehensive set of strategic procedures and bring them to bear on one problem. And that is very much like what happens in business and industry. When a problem crops up, there are many items, many things that contribute to the problem. And there may be many things that contribute to the solution. And creating an organizational structure to guide you through to that solution is very important. And this is simply training in that kind of thing. So you're really amplifying your organizational skills in going through the processes of investigating this. You're learning how to deal with this kind of complication in hopefully a comfortable way. Now, and it does turn out that organizational skill is probably more important than some advanced knowledge of math as you get farther and farther along. These processes here are not too difficult to deal with, but it's the organization of them that is vitally important in being successful in this area. You know, and it'll turn out that you'll find that in physics, when you get to physics, you find that a lot of times a problem which seems complicated can very easily be subdivided into many, many smaller, much less complicated little steps. And if you can organize those steps, then you can solve some extreme